workshop. The goal of this workshop is to discuss recent developments of multiscale feedbacks process on galaxy evolutions, and perhaps we can establish new collaborations after the workshop. That would be nice. So this workshop is supported by the National Center for Theoretical Sciences. Without NCTS, so we won't have the chance to organize this workshop. So we are very happy also today we have the NCTS director, Professor Thompson Zhu here. So let's have him to speak something and welcome all of you.
First of all, it's my great honor to be here to welcome you. I often do that because different organizers of different workshops ask me to as a way to welcome people. So I suppose we don't have a Zoom meeting today, so I don't have to welcome international people. I want to know what I have to say. He asked me to say a few words about the meeting. So of course, AGM is important. It is half Nobel Prize this year. For the other half, panels is on virtual work, which is for me it's like a black hole in space-time is not matter. So this part is still very important. That's why we have active galaxy thinkers we are talking about today. So the topic is very timely, important, and advanced. And I thought about when I was I was about to say a kid, but actually not a kid. When I was about your age, very young, in university, I took a course on astrophysics. And the things I learned about things like compact optics. Now I can say it. The keyword is compact optics, like neutron stars, supernovae, and black hole, this kind of thing. But they are more or less isolated. The lecturer is a professor from Canada. But he didn't talk much about the interaction and so-called feedback. It's very important. You are going to investigate today. So we study those things. Of course, it's important, but of course, it's more important to understand the big picture. So I thought about my own experience, another experience. Sorry, telling too many stories. As you get older, I think it's a tendency like this. Some of you have kids. When you have kids, it's exciting to see the scan image of your kids. But you only got to see them for a short period of time. Of course, if you have more money, then you can have a 4D scan and continuous monitoring. And then before the baby born, you can see as much as you like. That's the evolution. But more importantly, as your kid grow up together, and you see this evolution, then you can really see a lot of truth about life and about yourself, about meaning. Yeah. So I think probably in your mind to study the galaxy, to study the universe, is to understand the meaning of all this. Why in the future? I mean, you have so many galaxies, so it's not just one galaxy. What you come up with, your result today, will be able to understand the other galaxy, which in turn will help you to understand the physics for all these objects and the physical law. So this is a very important way to understand physics and beyond the traditional way of doing experiment, just like Galileo. I have some wishes for this workshop. So first I wish that by the end of this workshop, which is very short compared to the history of the universe, but anyway, I wish that by the time Andrew talk about this brainstorming, you will come up with a lot of good ideas how to advance for the next until the next Nobel Prize. And I also like to congratulate my colleagues in astronomy department. Albert is not here, but 6 years ago, there was a Nobel Prize on maybe 5 years ago. Chen was helping on gravitational wave. So that workshop was the workshop between Taiwan and Kaikoura. Yeah, it's a collaboration workshop. That's the first workshop discussing about the possible collaboration between Taiwan and Japan on this effort on detecting gravitational wave. That was a different atmosphere, different time. Kaikoura gravitational wave hasn't get any Nobel Prize yet. But anyway, the PI of that collaboration, Fujita-san, he accepted. He was contacted earlier on by our colleague, Chen, and many other colleagues also, in various meetings, and then he promised to come So he honored, he promised, and then came to Tsing and have this workshop that started initiating the collaboration, which I think so far has been very fruitful, but of course more fruits to come. So again, so they have done a remarkable job, my colleagues in astronomy. This time again, they just hit the Nobel Prize again, AGN. So now you're on an exciting topic again. So my congratulations and encouragement that they will keep doing this. Maybe in a very short time, you will have another workshop, which exciting workshop with more and more impact and fruit. Okay, that's what I want to say.
Thanks, Director Zhu. So before we start, I have a few announcements. The first is the session chair of the first section, which next actually originally it's me, but now we changed to Mengru, and I will be the session chair for the second session in the afternoon. And also today, this afternoon at 3 o'clock, we will have a group photo, which maybe the Candy will tell us like where exactly we should go. But remember, like 3 p.m. this afternoon, let's take a group photo. Okay. Yeah. So then maybe we can start the workshop, and yeah. So let me hand this microphone to Mengru to chair the section. Thank you.
Okay. So yeah, we will start the first talk, and then that will be given by Dr. Chen. And yeah, before he talks, I would like to spend maybe 1 minute talking about the schedules. So as you will see on the program, that like we have quite 90 minutes dedicated to quite a few talks. And then the hope is that during the talk we spend maybe like 45 to 50 minutes for the speakers to talk about like the recent progress and an overview of the field that he or she will be talking about. And we are hoping that during the talk or after the talk, there can be plenty of discussion. So for all the session chairs actually like a 90 minutes talk, we are hoping that some of you may prepare like the question list to excite potentially some discussions. And well, I did a bit yesterday, so hopefully let's see how it goes in the first one, and then we can adjust on the way. So. Okay, Ken's ready, so then let's welcome him for his first talk.
So, good morning everyone. My name is Chen from ASIA. So, first of all, I would like to thank the NCTS MMA group to organize these wonderful workshops, and especially the Chen and the Mengru, and to lead to making the program of the workshop. So today my talk is about the physics of the supernova. Actually, it's the physics of supernova at all scale. So it's not only about the exploding star, but how irrelevant to our topic of the workshop about the feedback on the galactic evolutions. So here you see these yellow bubbles. Actually, is exploding supernova engines. So before we talk about the exploding star, I would like to say about some of the background of the context. So this is a very awesome galaxy image, just face-on image. So you can see this very detailed structure of this gigantic spiral arms. And then you can actually see two kinds of different colors, at least two. So in this red one, actually those are the H2 region made by the massive stars. And then you see these dark colors actually is by the dust. And probably in the center of these galaxies, in the center of the galaxy actually maybe also holds a supermassive black hole, but in this case it doesn't have AGN for this example. So if flipped the galaxies, it's not only about the interesting about the face-on image of the galaxy. You turn to the edge-on image. In some cases, it actually also have gigantic structures like the outflow from the galaxies. And the physics of this outflow actually Karen is the expert on this, driving the galactic outflows. So what is the astrophysics within a galaxy? I would like to say the most interesting astrophysics phenomena actually occurs inside a galaxy. But the what? So we have actually starting from the basics, the star formation, how stars form, and the small or big star. For small stars, they have the AGB stars, evolved stars. For massive stars, they have gigantic mass loss and supernova. This is the central topic of my talk today. And in some cases, we also have these compact objects can emit these X-ray binaries. And the supernova and supernova remnant, and also the AGN at the center of the black hole. This actually galaxy is a twist of the star formation, interstellar medium, and stellar evolution, and tons of the microphysics is so rich to explore. So my topic focus on this massive star and the evolution and the supernova. So these are two images. One is this one is called actually also spider, look like a spider. Spider nebula is actually the attribute regime created by the massive stars. And then the other one is the formation of the massive star. You see, those are this shining bright object probably is the 100 solar massive stars. So massive stars are really important, although they are not too many, but really important in the cosmic evolution and the galactic evolutions. For massive star and the supernova, the motivation to study them because they are extremely bright, exceptional brightness and explosions. And inside this very massive star, they forge the very heavy element. It's not as heavy as the R process element, but those are heavy elements for the periodical tables. And also, they are actually also a nice laboratory to explore this fundamental physics, especially like general relativity, nuclear physics, and some even particle physics. More recently, because of accessibility in research, we are building more sophisticated models, and also observation help to really understand the physics behind these objects. But for galactic evolution, massive star and the supernova are the key drivers of the binary circle in the universe. So what is the binary circle in the universe is this. The gas. The gas first to condensate and then form the molecular cloud. And inside the molecular cloud, they start to form the stars. All kinds of different stars have different kinds of feedbacks to the universe. They can put out the dust, wind, explosions, even that the compact elements. And this also brings the interesting, for example, the gravitational wave, pulsar wind, and the X-ray binary, and supernova explodings. And all eventually those come out and eject into the interstellar medium and recycle even to drive intergalactic gas. This complete the cycle of the binary gas in the universe. So this is very important. This is show the example from my previous simulation, show the example of how one individual massive star and its impact on cosmological environment. So the size of box is actually a few kiloparsecs. And there is one only single star formed inside one of these cosmic structures. And how the radiation reshaped the cosmic structure of nearby gas. And how eventually the later supernova explosion and its energy and its metal try to influence the overall pristine environment in the early universe. And the plume of this blue bubble actually showing us a plume of the metals, how the metal comes out from the explosion and enrich the pristine gas. This metal from the hypernova explosion, for this example, actually can reach a size about 1 kiloparsecs. This is huge because inside these 1 kiloparsec objects, they contain many different microstructures. And those are structures eventually later will form the stars. And bring this to more realistic example. This is a movie done by my friend Jung from the Georgia Tech. And he is showing us a much larger version of how the first stars influence the early universe within a cosmic web.
Time-evolving visualizations give insight into dynamics that are impossible to understand from quantitative analysis alone. Only through simulation can we study this era. Early galaxies burst with new stars and flood the universe with light. The most massive stars explode in supernovae, spreading heavier elements, called metals, to their surroundings, promoting future star formation. Supernova explosions also drive star-forming gas out of their host galaxies, locally limiting star formation. The universe rapidly evolves as galaxies assemble. Over 15 million computational hours on a blue water supercomputer modeled gas, stars, dark matter, and radiation, producing a host of physical variables. Cool neutral hydrogen gas traces the dark matter that forms filaments and halos. The most massive stars produce tremendous amounts of ultraviolet light, ionizing the surrounding gas. The resulting clouds of ionized hydrogen reveal galaxies or stars have recently formed. Ionization, as well as shockwaves from supernova explosions, heat the gas. Heavy elements from supernovae enable gas clouds to cool, collapse, and form the next generation of stars. The combined physical variables show the anatomy and structure of the modeled early universe. We're now approaching an early galaxy only 1,000th the mass of our Milky Way. Though beyond the reach of present telescopes, the James Webb Space Telescope will detect these tiny distant galaxies. With its observations, scientists will be able to test if these large-scale computational models are capturing the essence of galaxy formation in the early universe.
Okay, so this movie done by John Weiss and his team actually showing the importance of how the first stars and supernova actually eventually influence the first galaxies formed in the universe. It's a huge computational resource to be used to do these calculations. It's quite amazing. So the key things going to the center of the topic here is we want to understand how stars evolve and how stars can grow as supernovas. Here just some introduction about the idea about the death of the star at all mass. If you have starting from this smallest mass, if we have the 22 solar mass stars, those is actually roughly the minimal mass to form a star. They eventually evolve into this brown dwarf and sitting there almost forever. For one solar mass stars, it's like our suns. They eventually will evolve and become later red giants. And the planetary nebulas eventually at the center will form a white dwarf. Note that the smaller star, white dwarf, sort of compact, but not as compact as I would say neutron star black hole. Then we start from 10 solar mass, things become more interesting. Those are the so-called massive stars. And at the end of the massive star, they either will become blue supergiant or red supergiant, and eventually have a good chance to exploding as so-called core collapse supernovas. And an even more massive star, say 35 solar mass star, similar to 10 solar mass star, but at the end, the center might likely to have a chance to collide into a black hole. And 60 solar mass also may collide into a black hole. For 150 solar mass, things will totally change because at least such massive stars, they into so-called clear instability regime and have good chance to exploding as a supernova, so-called parent stability supernova. Today, my topic will focus on discussing from the 10 to 60 solar mass star and the exploding mechanism. Actually, my thesis, PhD thesis, was write a lot of things, especially focused on this very massive star, about 150 solar mass stars. I don't have time to talk about these so massive stars. Just give you an idea about this, for example, these 20 solar mass stars. Give you some numbers, so the sense of favor. So our sun, for example, as a one solar mass star, actually it can live about 10 billion years. For 20 solar mass stars, actually the life is relatively shorter. The main life of the star actually from this hydrogen burning, so-called the main sequence. It can do this about like 10 million years in the main sequence for these stars. And then after hydrogen burning go into the helium burning, then we call the post-main sequence. The post-main sequence for helium burning in this case is about 1 million years. Later, carbon, nitrogen, oxygen start getting to the so-called more advanced burning. And those advanced burning actually from 1,000 years to less than a week. Especially from this silicon burning, this is at the phase of the star to evolve into the supernova. Just happened about 1 week. Very short. Everything very different in such a short time. So these are the idea about the time scale of the different nuclear fusion inside the stars. But how exactly massive star dies actually is a long-standing problem, and people have been studying this roughly maybe about close 40 or 50 years. People are still very active studies this problem. And one of the major concerns, people try to agree with the star can be exploding by the neutrinos. And however, this picture recently has changed a little bit. So let me tell you about something. So there are three different methods. Three different three different mechanisms to exploding a massive stars. So the neutron star, once the massive star eventually collapses, and from the neutron star emit the neutrino, can exploding the star. This is the first kind of neutrino-driven explosions. And for 10 to 20 solar mass, this mechanism may work well, but there's still some issues. And the other thing is, if you have more massive star, the neutrino is not enough. You need to borrow certain other energy, for example, the rotational energy of the neutron star to bore the explosions. And the third one is more exhaustive, is due to the explosion is borrowed by energy from a accreting black hole, so-called collapsars. This is actually because black hole is one of the most effective engines to produce energy, and then we think about it useful to do the explosions. So those are the things actually I learned from others, especially from two of my mentors. This is my PhD advisor, Alexander Hager. This is my postdoc mentor, named Lucy. And I'll tell you some of the recent developments. But let's check the standard model of the core explosions. Gaussian here is actually an expert on the core supernova explosions. And the Monroe is a neutrino expert. Those are actually two play important roles for exploding stars. And they show you what is the physical picture of the neutrino-driven explosion. One is the iron core, eventually the fortune of the iron core at the end, at the center of the massive star. This iron core will grow. It grows until the mass is about, say, 1.5 solar mass. It's what is so-called the Chandrasekhar mass. So the gravity of the iron core is much stronger than the electron degeneracy pressure. And so the electron degeneracy pressure is no longer able to support the core, then you trigger the collapse. And during the collapse, at the center is getting to form the total neutron star at a very early phase. Because this amount of energy, the collapsing energy, the gravitational energy was actually released in terms of neutrino. So neutrinos start to emit. And then eventually you form a total neutron star at the very center and getting more and more dense. Like an icicle, more and more hardened. Eventually material folding on this total neutron star will bounce back and generate a shock wave. In some cases, the shock can directly exploding the star. But in reality, most of the case is not, because the shock will propagate out. When you try to propagate out, a lot of energy will use, shock energy will use to do the photon dissociation of the heavy nuclei, especially the iron. So the energy was eat away. So the shock cannot propagate too long because it starts by this informal material. However, the central form the total neutron star to form a neutron star phase, it needs much more neutrino energy. Because the dense environment is very, very dense. So neutrino here is not really like a free stream out. It's more like a diffusion process. So neutrinos start to dampen the energy into this behind this soul shock. And that eventually drive the explosion to make the exploding supernova. So this is roughly the standard picture of neutrino-driven explosions. So the best idea is you can do the back of the envelope calculation is trying to do this. So the amount of the gravitational binding energy available for iron core roughly is about this amount, like 3 times 53 ergs of energy. This huge amount of energy, however, only about 1% of the energy is used to do the explosion. So neutrinos are able to dump into the material. And they emit the different types of favor of the neutrinos. Just as I mentioned, because the dense environment is so dense, even neutrinos have interaction with matters. So neutrinos try to propagate like a diffusion process to diffuse out. So here, just calculate the diffusion time scale. It's like just a random work. So, however, this opacity, actually the Monroe is expert on the neutrinos, and the different neutrinos have different favors, and different favor and the different energy have different cross-section and interaction with the matter that will affect how efficiently the energy can be put to do the explosion. And the idea here is the overall diffusion time scale roughly in this very approximate, like a few seconds. So just give you a sense of the favor. Star evolved million, billion years, but exploding only happened within a few seconds. Actually, in reality, it's much shorter in the most critical time scale. But the neutrino-driven explosion, when it sent out, and actually people will widely try to accept these ideas. But when the people try to do the real calculation, they encounter very different difficulties. So what's the major difficulty? These are the list of the difficulty. It's actually a tough physics. It's really tough. Because as the monk will say, with the nuclear physics, there are a lot of uncertainty on this, especially the reaction rate, for example. And also the equation of state of the neutron and proto-neutron stars. And also the neutrino opacities. So these are hard physics part. And the other part is Bochon's problems. It's a tough problem computationally. What's so complicated? Because you want to do this problem, you want to have a 3D simulations. And then you want to do a self-consistent way. You want to also have 6 favor of the neutrino. And then you want to solve this with Boltzmann equations by considering the multi-energy group and multi-angles. So this is a huge computational challenge for most of the people at this moment. And the third part is they also relate to some of the other physics like a magnetic field and the rotation. But this is a more related new part people are exploring more and more at the recent time. And if a black hole forms, things will actually get more complicated than before, because you need to consider the general relativities and in your magnetic hydro equations. That's also really hard. So those are the things, the details, try to calculate the self-consistent co-collapse neutrino-driven explosion difficult.
Can you say more why magnetic fields and rotation are important?
Yeah, I will explain later. This is some detailed. Yeah. So the central engine is the key. So central engine here, I would say, and at the end of explosion, there will be a neutron star or black hole left behind. Actually, how exactly whether the star can explode, actually very sensitive to 2 of these relevant compact objects. So this is just like I show you the movie at the first page of my talk. This exploding bubble showing how the neutrino-driven explosion plays a role in the real 3D simulations. This still use the approximate simple approximate neutrino transport in their calculations. It's not yet actually considered for neutrino favor, even the favor neutrino oscillations, or even about the general relativity here. And this is a successful explosion. In here, even because people used to do 1D simulation, and recently with developing multi-dimensional simulation with the help of the supercomputer, people are building from 1D to 2D and getting to these 3D full physics simulations.
Sorry, what's the speed of this movement?
The speed of this movement, actually, at the end of the exploding the shock, this is the very center of the stars. Just show you when the core collapse, when the central ion core collapse, and then neutrino driven to revival, I show the Stokes shock and the magnetic explosion. Actually, it's very slow at this time. I would say it's 10 to 8. It's about 1,000 kilometers per second at this scale. But later, when the shock propagates outside, you're getting faster and faster. And then when eventually all the explosion occurs, the average travel velocity of the supernova explosion, say roughly like 10 to 4 kilometers. That kind of scale, 10 to 4 kilometers per second. So if you successfully exploding, then you will see this. This is a supernova element. You will see an explosion. And this is a much larger scale. An explosion happens much later time. If you fail to make the explosion, then you will see this. Not exactly this. A very much small scale factor, kind of factor of million, ones of the million. Much smaller is a black hole. However, there used to be when the black hole formation, we don't feel that interesting because At the early time, we don't see anything at least for black hole. But recently, with the detection of the gravitational wave, things getting really interesting because Chen actually also calculated how the gravitational wave collide from the co-collapsed supernova, and possibly might be able to detect by the Cobra or LIGO if that co-collapsed supernova occurs within our galaxies at this moment. This is very exciting because it really opened a new window to prove the physics of how proton neutron star become a neutron star, and how the neutrino emit, and how the oscillation equation state of the proton neutron stars. This is really exciting. But I want to tell you the truth is, for the neutrino-driven explosion, probably if you have a massive star about 20 solar mass, things probably won't work because people try really hard, but it's just really hard to actually exploding 20 solar mass star. Just a complication from my previous mention about all the physics and the computational difficulty. And probably we are missing the wrong physics too. So people now shift the paradigm a little bit to think about respond to exploding a 20 or 30 solar mass star, or even more massive star. We need a different engine. And those are the engine need to drive a very extreme, powerful explosion. Sometimes we call the hypernova. And the idea is here. The central engine here form the neutron star or black hole. Most are compact objects will be able to have a good chance to provide a very extremely energy to drive the explosion. And that explosion is not just like a hydrogen bomb. It's not no longer like neutrino bomb. It's like a homogeneous explosion. It's now because these are the engine might be associated with accretion of a black hole or emitting from the central neutron star, especially called the Magnetar. I will discuss later. They will drive very powerful explosion in a very anisotropical way to make back explosions. And you might have the jets, you might have the winds, and how exactly this kind of structure looks like, needs to further explore. So people are getting very interested in this. And those are the engines. For example, the jet will power so-called gamma ray burst. And gamma ray burst is highly beaming radiation. If you observe a gamma ray burst, that actually you can see the gamma ray burst from redshift about 10, from really high early universe. And that's a very powerful tool to prove the early universe. And also how exact jet, how the magnetic hydrodynamics and general relativity equation state of the neutron star plays a role. It's a very sort of exciting for the fundamental physics, like among the other nuclear physics to explore. So I tell you about just like Zheng Yu just mentioned about how magnetic field and rotation try to play a role in the explosion here. The idea is here. The rotation, actually, if you have a star, here so-called Magnetar. Magnetar is a rapidly rotating, strongly magnetized neutron stars. So those are the extreme energy of the neutron stars. And because those are the magnetar, they're rotating at the millisecond scale. It's really, really fast. You times the neutron star mass, 1.5 solar mass, and the rotating at the radius about 10 kilometers, and at 1 millisecond. This amount of energy actually you probably will get is 2 times 10 to 52 Earth's energy. This energy is about 20 times larger than the typical exploding energy of a co-collapsed supernova. There's a huge amount of energy available at the neutron star. But the key question is how you get that energy out to do what you want. This is the key question. Then here we need the help of the magnetic field. So magnetic field like a string attached to the neutron star. So, or you can think like a brake. So neutron star like a wheel, it was running and running, and you have a brake. And you can use that brake, magnetic field, to tap out the energy, tap out the rotational energy from the rapidly rotating neutron star. This is how you get the energy out. So that's why you want to have strong magnetic field, because more stronger magnetic field, stronger brake, and more efficiently to get out the energy. And here, if you just simply assume, actually it's more complicated here. So you simply assume the magnetic field is sort of like constant. And you can, using sort of the dipole formula, try to extract how much radiation energy can be get out, dipole radiation from the neutron star, in this case. So it's about 10 to 49 ergs per second in that kind of scale. So this is extremely useful, and this is one of the favorite models so far for many different supernovas. I will tell you something about later. So actually, it's solve a little algebra that you can get how the rotation period, luminosity, and the energy of neutron star in terms of this current, this spin down time. So this is the best idea. I want to get the explosion out, but the neutrino cannot do the work. Now think other way. Now no, there's a possibility neutron star can rapidly rotating and contain a lot of energy. Then we have magnetic field very strong. Then let's use magnetic field to tap out the energy from the neutron star to help us to do the explosions. So that's the idea.
Sorry, stupid question. Where does the magnetic field come from?
So this is actually a complicated problem. It's really complicated. People are really studying because actually one thing you can think about easily is star originally have the magnetic field. And you can think about when he collapsed, the center of the star collapsed into a neutron star. All the field line was sort of like frozen. You think about flux conservation.
So it's not coming from plasma rotation?
In this case, we don't need plasma.
Oh.
We don't need a dynamo at this case. Yeah, we just need flux. Make all the flux streamline the field line to compress, to contract into the neutron star. Then we have large enough magnetic field.
It sounds like it's a static magnetic field instead of dynamic.
It's actually dynamics. Actually, it's
Well,
where it
it's
comes from.
frozen, then how does it become dynamic?
But actually, actually, it's more like a condensed matter nuclear physics, because basically there's a Nature paper about this room temperature of the superconducting material. And I feel it's really exciting because people say we need to have used to the high temperature superconductor need to have at least minus 20 degrees to do this. However, they do the room temperature 15 Celsius degree. It's quite a tremendous improvement, but the people say, oh, you need to do with under super large pressure to do this superconducting. But I was actually thinking about the same problem is, I think neutron stars have a super large pressure at the center. And the super large pressure make that easy to form to become a superconducting object. And that superconducting object will be easily, I think, if the charge is not totally, completely neutral, or just a little bit, might be able to generate huge current. And that might be also to explain about a little bit of the strong magnetic field line. So the key question you asked about the field line, the magnetic field, actually the magnetic field my naive thinking is relate to the rotation of the neutron star because it depends on the also in the essential current and how it dissipates and how evolve, how its morphology is largely unknown. So there's a little bit a lot of microphysics can be studied here.
I'm not sure if the superconducting phase will play a role here, but I think for formation of some magnetic field, maybe motion can say it. Like, and then because in the study, that people tend to say you go through like the magnetic rotational instability to amplify the signal magnetic field.
So if just assuming like flux conservation, you have B divided by pi r squared, if it's conserved, then yeah, that can provide some magnetic field. So most importantly is after pole bounds, because things it's become convective due to neutrino-driven convections and also proton neutron has convection. So there are also people studying during this process, magnetic rotational instability can be happens, and then in that case, magnetic field can be further amplified, and maybe we don't know yet, maybe enough to power hypernova.
Just simply from flux conservation, then we need the initial magnetic field like into the 9 gauss inside the star. That's probably good to
Huge.
Yeah, I think this because like some people, the fields, some people are working on try to do the dynamo model for this to simulate actually the Magnetar formation from complex simulations. And then actually they really encounter a problem is you want to form a Magnetar in your simulation. Actually, the initial seed field is still need to use a very big numbers. Yeah, because it's still under debate. So people are still working on this. Yeah.
something like 10 to the 11 meter.
Yeah.
So one more question. So how to know the time dependence while simulation or
How to know the time dependence?
is the bracket is the t over t? Yeah. Is that time?
Oh, this one?
Yeah.
Oh, this one? Oh, this is actually the spin down time. So actually, it's sort of do arrangement. This relates to the rotational period and the strength of the B field. This 15 is 10 to 15 Gauss as a unit. So it's just like a characteristic spin down time from this type of radiation.
It's a same type of radiation.
Yeah.
Right. It is having a field. This maybe still final classification.
Yes.
May not be exact.
Yeah. Yeah, this is a single dipole formula. Actually, it still have much room to improve. So actually, I've been thinking about different ways to try to do this later. And tell you about some of the explosion. So we just discussed about the neutrino-driven explosion, and also with hypernova explosion powered by the central magnetar, or possibly by the collapsing or collapsar by the accreting black holes. But however, those explosions, what observers, what we really see, and how we really know about physics? It's just a series models and just play for mathematics or computer game, simulation game. No, that's not actually the case. So the model eventually need to compare with observation. But what's the gap? In the early time, everything from paper and pencil calculation and then evolved into the one-dimensional simulation like 30 or 40 years ago. And in especially recent 1 decade, people start to explore with 2-dimensional, 3-dimensional simulation, with good simulation, getting more incorporating and more microphysics to do these things properly. However, those need to be compared with observation. So what's the gap? The gap is that explosion itself is just discussing about what the engines, what's the possibility where light explosion occurs. And those are all the physics. So we model, getting from the model, we get the numbers from the density, temperature, of different elements from this. And then when we observe, and we didn't observe this, we observe lines. So this is actually the gap. So actually my work is trying to connecting with how this angel explosion, try to make a link to these observations. Those sort of associated with some of the radiation calculation to do this radiation transfer or transport to get down exactly how to predict the observational signature from the different models and then compare with observations. So let's learn about the supernova observations. Actually, we have the expert Chen is here. He's really the world expert of supernova observations. And sorry, I want to use this slide. So this is a supernova. Supernova explosion. Explosion is just a period, very short time. It's a transit. It's a transit like a firework. And this example is one very beautiful example. This is a galaxies. It's one exploding supernova here. This is actually quite significant. You see, a galaxy contains billion or 10 billions of the stars. And one supernova can rise to bright enough to compare with the galaxies brightness. It's quite substantial. So, and how we really understand this here, this so-called light curve. So you measure the sky, and scan the sky, for example, every hours. And you suddenly see an object from invisible and to bright, to rise, very bright, and gradually decayed. It's so-called the light curve. We see it's a transit. So in this case, like roughly 100 days of this transit, and it quickly will disappear, just like our fireworks, something bright. And the most information is getting from the amplitude of this brightness. And also another thing called the spectrums. The spectrum of the supernova light curve. The spectrum was emitted from the different atomic or molecular transaction lines. And those lines contain very useful information, tell about the content of the supernova. So this is very important, very useful, like a fingerprint. So fingerprint will tell you very detailed about these explosions. And try to understand about the light curve is, you think about the light curve, you think about the peak, how bright it is, what's the peak, and how long it lasts. Just 2 parameters, and you learn a lot of this. Let me show you. So, you understand the supernova light curve. Then you join this, just I mentioned the light curve duration in this x-axis. Peak luminosity in the y-axis. Most of the cloud collapse from neutrino-driven explosion or some hypernova explosion actually from this around these corners. Type 1A explosion is about brighter, a little bit brighter, but a little much shorter in time. Recently, it's very interesting. This is more to the recent development of the field. Recent years, people start to discover the so-called superluminous supernova. Those are the supernova you look in terms of peak luminosity. It roughly actually older, or maybe 2 order of magnitude more luminous than those core collapse and type 1A supernova. That's substantial. And those are so-called new category superluminous supernova. Another thing also being very interesting and people study is so-called very faint supernova. Either very luminous, also very interesting. Either very faint, also very interesting. Those are faint supernova, also including one of very exciting discovery of something like a Supernova types is faint rapid transit contain a lot of interesting, exciting information as well. Then actually later I will show you what we learned from this. The light curve duration, how you make a transit last longer. So you want to last longer, that means the photon need to diffuse gradually in a much larger time scale. And you need to, what you need? You need a more massive of the ejectors and more opaque of this in the ejector, more longer diffusion time. Its peak luminosity always also reflect more energy of the explosion and the large radius of the photosphere at the time. Then let's try to do the back-on-level calculations. So the idea is how you understand the supernova light curve. Try to do this way. So the idea is a diffuse time scale. You think about the supernova exploding, and eventually you expose to some radius. And at that radius, the radiation starts to come out. So at the time, when the diffuse time of the photon is equal to the expanding time, expanding ejector, it's roughly when the light curve starts to appear, to rise. So this is very approximate. You assume the sphere and the mass and the temperature, and there is an expanding mass. So the V is constant. So you do the expansion time by the radius divided by the velocity, and it's an expanding time. And those are the second, the T diffuse, this is diffuse time. So random work. How photon need how much time to propagate, like a neutrino, very similar to neutrino, to propagate to the radius to R. So that's associated with the mass of this ejector and also the opacities, also the radius. So you put in the number, rearrange, then you get a supernova time scale roughly by equal these two parts. Then you can get the velocity, you can do this exploding energy divided by this mass and square this velocity, kinetic energy. And it is a supernova time scale. Then you put in all the number back into this. Then you roughly get the supernova light curve time scale roughly 30 days, roughly a month. Really depends on the mass of the ejector, the opacity inside is also the exploding energy. You more massive, more diffusion, take much diffusion, longer diffusion time. The supernova light curve length longer, more opaque the same. If you the exploding energy is faster, so that expanding much faster. So you need to shorten the duration time. And then you can also calculate the luminosity by the amount of variable radiation energy by the diffuse time. The little range of the algebra that you will get is about 10 to 41 ergs per second. So that's roughly the idea about luminosity of the bright of the supernova. So I want to just talk to you about some more recent developments. And what's really interesting here is all about black holes. So this is the example so-called faint or weak supernova explosions. Because I tell you, the original catalog is the bigger square collapse and type 1A. And more recently, interestingly, put into the supernovae and the faint one. And these are the one model I'm working, I published before, is so-called faint supernova. Faint supernova explosion is just very magnetic explosion occurs. So the energy, the explosion is not very energetic. And the resulting, the light curve is not very luminous. But then you have an interesting feature, is like here. So those are, you think about this, a quarter of the stars. Just quarter of the star. And that explosion just occurred. it's eventually, the shot still eventually launch, and you propagate, eventually still break out the entire star. But look at this very central part carefully. Since popping out, however, due to there's a central neutron star there, and the ejecting energy is not very strong, so inner part will suffer a lot of gravitational pull from the central neutron star. So what happened? The material will fall back, once again, the material will fall back onto the central neutron star. That eventually create a black hole for this case. Because LIGO recently have been detect a few of the black hole candidates and raise a very gigantic interest in the community about how certain mass of black hole actually form in the stellar evolution or in these supernova exploding channels. And here I just show you one of the ways you first form, you do a successful explosion, but you first form a neutron star. The neutron star later actually will turn into black hole due to the fallback of the material.
Does this depend on the metallicity?
Yes, this depends on the metallicity. But those are the model very special because you need to have a stellar structure will barely allow you to launch the shock. And that shock can propagate eventually throughout to break out the star. But because the energy, exploding energy is weak, the inner part has received amount of energy very small, so kinetic velocity is small. And much of then part of the core cannot have getting an escape velocity from the central neutron star. They start to falling back. Actually, those kind of model originally was developed to explain some of the so-called metal core star abundance, EMP, extremely metal core star abundance. Those are very interesting stars because we believe those are the stars because we use extreme metal core star to prove about the origin of the first stars. And that show a very interesting abundance pattern. Cannot be easily explained by the normal corpuscular explosion. They need either hypernova explosion or they need either this kind of weak faint supernova explosions. And those are actually these are I've done a few models to of this example. This is actually the 60 solar mass POP3 star, the first star, eventually leave a 6.8 solar mass black hole at the center.
So, is this neutrino-driven explosion?
Yes.
Oh, okay.
These are neutrino-driven type explosion. Yes.
So
it's a symmetry explosion.
So the turbulence come from neutrino.
Oh, good question. Actually, the turbulence is not from the neutrino here. The turbulence here is from the fallback. So let's see the movie once more. So when the shock, actually when doing the explosion, they actually really some explosion were driven by the turbulence, but most of the turbulence were driven by when the Tsing goes upward, but they will be pulled in by the central gravity of neutron star. They've been driving this so-called, these are the fallback. So it's more like a kind of the Rayleigh-Taylor instability.
I thought here you put like a piston.
Yeah, this is actually we do the both model, two models. So one is from the Kepler model. So the Kepler model now also have the 1D neutrino driven explosion, but it doesn't have a fluid instability. Yeah. So they use the explosion model actually most of stellar evolution will be evolved in the one-dimensional case. And until the last stage, they will be taken from this 1D model and do the explosion. And because Thomas Youngcar and Woosley, they have some collaboration, so they put in a 1D neutrino explosion in the Kepler model.
How do they do it?
They just emit the neutrino LIGO from the 1D boundary. They think this is much, because they want to do the nuclear synthesis correct. But the explosion, I would say, is not still the best. Because 1D explosion for neutrino is not maybe not efficiently work. So
usually when I decide like star surface, additional put some energy as contribution.
Neutrino flux.
So it's similar to the push project.
Yeah, but
there are some neutrino flux is put in my head.
Yes, that's why neutrino put in by assuming there is already the pro-neutron star form and emit a lot of neutrino flux and getting on the inner boundary to get out to drive the explosion. So another area type people just do a piston like to push out the material. So neutrino is a sort of improvement because the nuclear synthesis during this explosion will be they want to do nuclear synthesis more properly.
But actually a little bit confused.
Yes.
In your movie slides, initially you have a spherical explosion.
Yes.
Later on, are you continuous still dumping some energy in the center?
No.
Only at the beginning?
Only at the beginning.
Then how you model this? So they only compute mass
this is the case is this is just all the neutrino dumping. Just you think about it, sharp revival already.
Yeah.
So the snapshot here is study already sharp being revived. So sharp is propagated, and that's then evolve in this 2D model. Yeah. So there's no additional neutrino or other energy dumping in this case.
So you deep check all the J-card and then you simulate until the fallback.
Yes. That's the key of this simulation. So just want to see how the ejecta be evolved, how much ejecta be thrown out, how much ejecta will fall back, and how much the mass will accrete on the central neutron star.
This 6.8 solar mass black hole is the mean mass. Because the fallback is
Actually, it's quite close to the final number because simulation evolved a really long time. So just see some of the material coming back until most the inner parts become like a vacuum. So sun's out already far away, and the creep is almost already come to the neutron star.
If you have black hole,
yeah, that's a good point. That's why here we don't consider the black hole feedback, but it's likely to have a case with accreting is not only about adding the mass, but maybe adding the accretion or the accretion power from the central black hole. They might be powered to influence the more large scale environment to affect the fallback. That's likely true. So let's continuous about this part. So I just show you one of these example about the weak supernova or faint supernova. However, there's another type. Those are Magnetar powered supernova explosion. These are the exploding stars driven by the Magnetar. But I want to say something first. So this is actually a solar mass carbon oxygen core. So you think about the star originally from a 35 solar mass star. Then it goes through the stellar evolution and mass low. Eventually everything left behind is a solar mass, a carbon oxygen core. And inside the central carbon oxygen core, there's still helium and other silicon, other layers. And when that core do the explosion, because if you want to do the core collapse wave, there's no way I can draw out the star unless you have an unrelaxed neutrino energies. Let me see, a little bit fast. So here the explosion is not due by self-consistent. I mean, we do the energy by injecting the explosion energy based on the dipole formula I just calculated in the previous slides. And here is a hypernova, and I'm putting all the energy along the z direction, the polar direction. And I want to see how the explosion engine and the explosion geometries try to influence the ejector. This is also quite interesting and substantial because when you do have a jet, and that jet usually will travel very high speed, like close to the speed of light. And then when you break out, that will likely to have you have a gamma ray burst, a so-called long gamma ray burst. So it's about 10 to 20 seconds. A huge amount of energy beaming in the direction of the jet. And that simply blow the star. But simply just like shooting a gun through the apple and completely destroy the apple. And this is like a very similar idea. And however, there's other interesting thing. I just say all the energy will beaming through the jet. The jet is actually really easy and powerful enough to completely destroy the star. But the jet will launch, but in the z direction. However, what happened? The cloud is completely spherical all the way through the center. And this central neutron star collapses. And on the other side, around the craters, material still accreting into the central neutron star. And in the end, this guy also turned into a black hole. So this guy from 8 solar mass carbon oxygen star turned to 4.54 solar mass black hole. So there are many black holes. Even they are explosion. They are black holes left behind in the explosions. So
in this relation, you go back one slide. So the ambients are like static.
The ambient is static. Yeah, but very. So the way we do this because we simulate in this European Podium. So there are much of the objects. So those are 1D model from the stellar evolution model. Take the star. But we need to simulate in the much larger scale. So we need to put in sort of ambient density and other things. So usually try to choose extremely low and try to minimize, try to mimic like the stellar environment. That would be the idea.
Put the Magnetar into like some cones.
Yes, yes.
Well,
the format. The format is this one?
Is it from the previous?
Yes, yes.
To have some spatial in the boundary of the center.
Oh, okay, this is a good question. So actually the way is there's a central neutron star and the jet emit on the pole, this like pole, jet from emit, and the inner part is like a hole. So like a material can flow in.
So you assume some like accretion.
Yes. So this is very energetic. Okay, this is some more detail here. So the jet exploding and the propagate. However, the jet, they launch out the jet. They actually create a cocoon. So there's a sine wave or shock wave. They propagate along the way. So eventually, when this cocoon eventually merge at the equator, all the accretion will be stopped. So this is actually how the inner accretion is stopped by this, in this mechanism. So not just because you launch in the pole, then no one will stop the equator. Actually, not in this case.
And in this simulation, do you assume that magnetic field at that location for this 8 solar mass object?
Yes. No, at the most in the
That's not realistic.
No, not the case. I told you this number is for the central engine. So central engine. Oh, that's good. So you see this size of this scale like 10 to 12 or 10 to 11, 4 times 10 to 11. The central neutron star here, radius 10 kilometers. And the most is inner part simulation. I get down to the resolution roughly about 100, a few hundred.
So you started with X solar mass core, which contains a neutron star or what?
No, there's actually some more details. So this X solar mass core stars is evolving beginning from 35 solar mass star at the end. And at the very center of that stars, start to collapsing, iron core start to collapsing into a neutron star. Then at that time, just remove the most inner part and replace the inner boundary condition to do like the explosion. An inner boundary condition, the energy and the size actually is energy doing by this formula. Yes, that's the source. It's not entire star have this kind of gigantic magnetic field in the energy.
Okay. And also, how sensitive is this rotation? I mean, 1 millisecond for usual 10 kilometers.
Oh, good
That's
question.
not possible, right?
This is a good question. So I mean, Magnetar has an intriguing properties, and the one is in this case, you want to rotation period less than 1 millisecond because you want to have energy exceeding 2 times 10 to 52 ergs of exploding energy. You need a lot. You want to have a lot of energy resolved in the neutron star. The B field is more critical here. The B field here will decide how fast you can get out the energy. The B field is stronger in this kind of hypernova case. The B field must exceed 10 to 16 Gauss. Otherwise, it is below. Otherwise, the collapsing neutron star will continue to collapse and eventually merge into a black hole. Because you need to sort of release a lot of energy in such a short time. So that's why very sensitive. And later I will tell you this can do other things later, but I don't have time. I don't know how much.
Go ahead.
Good. Sorry. So that's sort of like a little bit move on to another interesting and active research area in the supernova community. Let's just talk about very faint. How about something very luminous? Not very luminous, so-called superluminous. So those you see all these lines. Those are the different types of supernova, including core collapsing type 1A. And these guys, 2006 G1. Oh my God, it's almost like a 2 order of magnitude more luminous, even at least maybe 1 order of magnitude longer than some of these supernova. So this is huge. It's bright. So the question is, how come we do the explosion in the same way? How come this guy is much luminous? How does that happen? So this really need to think about here. I told you, remember after this talk, you need to remember only one number. The explosion for core collapse supernova or most of supernova is 10 to 51 ergs. And the superluminous supernova has a radiation budget 10 to 51 ergs. That means all the energy for core collapse need to convert into radiation. However, it's not impossible for the normal supernova to do this. So how you get such huge amount of energy to radiation? Explosion itself unlikely because you get enough energy, but you got to share with the gas energy and the projectile energy, kinetic energy. Neutron star got megatons. I tell you very quickly. Otherwise, you need a lot of radiative decays. So that's one of the experts on these decay isotopes. How much energy can release and how long it releases. And in this case, nickel 56 is usually popular for supernova community in 10 solar mass of nickel. But just say that's an explosion like a 10 solar mass, then you turn 10 into 10 solar mass of nickel. That's difficult. But another way, so-called pan-stability supernova might be able to do it. Is the thing also popular, but the modeling recently difficult is do the shock and the ejector and certain state material interactions. That will actually be able to convert energy into the radiations. So, superluminous supernova, again from Magnetar. Originally, idea is from a few folks. Keiichi Marita, Dane Kirsten, Bill Gaston, Asbjørnsen, and Stan Woosley. Those are the earliest papers about suggesting, oh, how about let's use Magnetar to do other things than explosion. Let's do the power of the superluminous supernova. But how does that work? You think about the one key things. You need a huge amount of energy, not at the beginning, but at the late time. For what? For power the radiation. So you want that energy not come out so quickly after explosion, because otherwise you will simply absorb by the ejector, and nothing will interesting will come out. All the energy eventually convert into the kinetic energy of gas, and things just moving very fast. But moving fast doesn't mean they are luminous. So those are the first. So look at check these numbers. So this number. If you want to do Magnetar luminous supernova, then the B field you need to down to 10 to 14 Gauss. Why? Because I still have Magnetar, still have a lot of gravitational energy, but I don't just want to spend all the energy at the very beginning, at a few fraction of a second. I just want to keep it later, then get it out to radiation energy to the data. So these are two observational example from this the PDF surveys. Much effort from my part has been spending how to understanding the superluminous supernova, especially in terms of multi-dimensional simulations. Those are the previous 1D model. They're perfectly able to produce a light, but if you are in the market, you know actually there's something look bizarre in that 1D model, but no one actually showed. Because this kind of luminous supernova, they drive a significant amount of fluid stability due to the radiation pressure of the ejector. But those are not 1D model can be done. And these 2D example I done like in 2016. And here I show this a successful explosion of the star. And the central magnetar drive the energy, strong energy to push out this ejector. And this is the bubble for energetic energies. And in this 2D case, actually, due to the strong instability on Earth here, will break out this shell of the ejector and release out the energy. This is very new insight of the model just presented here. So in previous 1D model, no one actually will be able to predict so-called the radiation breakout signature from this Magnetar power supernova. And more recently, actually this year, I spent millions of CPU hours and working on a few years, eventually make this power 3-dimensional superluminous supernova model. We simulate from very small, this is roughly the size of the neutron star. So we simulate from very small regions. And the entire effective resolution for like 3D simulation is 1 million times 1 million times 1 million. So then we start from very central engine of the explosion. Then we expanding the simulation eventually to a very large scale. Because we want to see how eventually this tiny structure of neutron star play a role on a large scale of the supernova explosion and how they influence the observational signature of the supernova. Supernovae is supernovas. We actually discussed some new kind of mechanism to drive the mixing and eventually be able to explain some of the models from the observations. I think it's a quite interesting model. This almost come to the end, so this is a summarize of some of the mass and the black holes, because now we have gravitational wave detector, we can see the black holes. So we want to use this to prove some of the black holes. There are some details, however, those are from the models still have suffer a lot of uncertainty, like how the mass loss in the star, how rotational play a role, convention plays a role, and the explosion itself is a multi-D issues like explosion engine and fallback. Finally, give you some of my thoughts. We studied the supernova and try to understand how they feedback on the galactic evolutions. But what's the key point we need to take? Here, we want to model the feedback correctly from supernova. We need to understand the initial mass function. How mass distribute, how mass star distribute in a certain environment, in a galaxy or in a GMC. And how the stellar physics plays a role, affect the evolution of the stars and the supernova. This is all key. And also the explosion mechanism itself. So the final remarks is massive star and the supernova are really critical because they are key driver of the Baronic cycles in the universe. And I show you some of the importance of the fallback and also the mixing during the explosion. They cannot be ignored because they used to be ignored, but they cannot be ignored because they not only play important role in the observational signature, but also the abundance patterns from these ejectors. And now we have a gravitational wave detector open a complete new window to prove the very early phase for the core explosion, which Chen is now working on from localized gravitational wave. The metal yields also help us to trace the stellar population of this massive star in the galaxies. The final thing I don't have time to talk about is, in most of galactic simulation, the feedback actually, the resolution and the physics can be model approved to become more relaxed to put in the galactic simulation models. So that's my talk. Thank you very much. Any question?
Thank you very much. Very nice talk. So
Thank you very much.
Physical environment of superluminous supernova.
Yes.
So observationally, the host galaxy superluminous supernova shows very different property compared to the normal galaxy. Very metal core.
Yes, yes.
So even more metal core than gamma ray galaxy. So does your model require particular metallic environment to produce supernova?
Yes. I think this is a very good question. And the observational part, actually, the Pioneers just sitting behind you is actually expert on these host galaxies. But then I tell you about the model part. So because low metallicity is very essential, at least for supernovae and supernova. Because those are actually the stars you really need to get out from massive. Not normal massive. You need, I say, about 20 solar, maybe 30 solar mass stars. And not only at the beginning, but at the end. Because star lost mass during the evolution. And the metallicity plays a key role to drive the wind. So as long as the metallicity is low enough, then you were able to maintain or keep more the mass at the end to help you to evolve into this stage I just mentioned to power a supernovae and supernova. Yeah.
So in that sense, both metallic environment and magnetic.
Yes. Yes. Yes.
Thank you.
Yes.
Thank you for the talk. So I have a general question for simulations for
Yes.
supernova.
Yes.
Do you apply, do you consider background space-time is flat throughout the simulation?
Oh, yeah, that's a key, interesting. I think there's, for core collapse, supernova, or at least the model I'm working on, actually, those models I just discussed, I don't have a GR here. I don't have to put a GR here. But however, if you like doing something like what you're not doing, try to calculate gravitational wave from proto-neutron star, then you need a GR. But how precise the GR, maybe fortunately you can comment a little bit about this.
If we are looking to the much inner scale of the supernova engines, then definitely GR is very important.
Yeah, in that case, do you consider GR MHD simulation?
Yeah, most people consider GR or at least post for supernova engines. Because that was previously, maybe 10 years ago, most simulations are still doing Newtonian calculation. People actually found that if we don't have GR, then the neutron star won't be that compact, and then GR effect can actually further boost the neutrino heating efficiency, and that can help to get explosion. And so if you want to get a successful explosion, then GR is one key ingredient to boost the energy.
And just one more question, maybe for both of you. So usually what is the condition for black hole formation?
Okay, that's also a good question. Here we just assume, in here, when once my neutron star exceeding 2 solar mass, I will assume it turns into a black hole, at least in my model. So, but I just use the mass of the accreting mass on the neutron star to decide whether this is a black hole or is a neutron star. This is in my case.
So how will you change if you change the threshold up to say 3 solar mass? Will that change a lot your result?
No, it won't change a lot. Just whether I define whether 3 solar mass black hole, 0.1 or 0.5 or neutron star, or in between like a sort of massive, hypermassive neutron star. Because it is very uncertain about the, maybe Mono is also expert on answering the question, is that the equation of state, of the neutron star, that will determine how compact and what the mass, maximum mass he can reach. Yeah, that also depends on whether you considering about its rapid rotation and whether it has some, how much neutrino cooling and efficiency. That's the detail of the nuclear astrophysics, the microphysics. But definitely, at least I think the 3 solar mass black hole, 3 solar mass neutron star probably we didn't see, at least in observationally or in model, maybe also very challenging to make. Yeah. So just say it's a black hole.
And also how fast it's growing.
Yeah.
And also in your simulation, like either neutron star or black hole, they contribute only greatly.
Yeah. Yes. 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 Yes.
I noticed you use a millisecond method to power the exposure, but is it realistic? Because all the observed Magnetar only has a period of about a second.
Yes. This is also a very good point. The thing is like this. In the dipole radiation I just showed you is, I use that dipole formula to calculate amount of luminosity or energy output from the neutron star. How much energy, how fast can it extract from the neutron star. But I would say in that case, the dipole radiation probably won't work in this extreme magnetic field case. And I'm likely to assume actually the magnetic field actually goes through from a hypernova model, from this 10 to 16 Gauss and 1 millisecond case, it will be evolved. So you first have a very strong magnetic field, and you quickly extract a lot of energy from the magnetar. And the B field evolve with time, become more gradually, and also the rotational period also become much slower. So when we already observe aftermath, already far long after it become a kind of critical stage. The critical stage is short, just as like a transaction from this magnetar, extreme magnetar case to the normal magnetar people observes. That's my thought. So I try to make the model to making the model from how I make a hypernova explosion and also make a supernova. Try to make this kind of combined model. But however, because there's uncertainty about the detail of this microphysics of the magnetar. So here just more like a play with some of the parameters in here. But I think people are working, plasma physics are working on making this magnetar model become more realistic. I believe there will be also some breakthrough in this part.
But do you do any calculation to estimate the decay time scale from millisecond to second? Is it consistent with the observations?
I think this, because the spin time scale from dipole radiation tells us our time scale is still much shorter than the observation. Yeah, in our case, yeah. But I think, okay.
The stars are actually traveling the median at pretty high velocity, like
yes.
a few kilometers per second. And so if you introduce a velocity into your background median, will this have some potential impact on the instabilities related to the explosion?
Actually, no. The reason is here. The reason is here because actually, I tell a story. I used to work with a German advisor, and German are very picky, in some sense. So when I do the explosion, I want to make the explosion from my 1D model, and my professor said, no, that's not realistic. There's a massive star, there are convecting zones, and you need to think about how to make a way to make the convecting zone inside your multi-D model. Then I spent about 1.5 years something to make this kind of I call turbulence perturbation models in my simulation, but eventually the result doesn't change. So actually, because the shot should travel much faster, and when the shot travels through, originally might have some turbulence region, and the shot seems to actually, because shot is over-dominate, and it will smear out, smash out these structures. So there's actually very, very tiny little trace of the structures from the previous turbulence environment or convection zone inside the star. Yes. So
basic question
yes.
About the SME feedback.
Yes.
One is that often people say 1 times 10 to the 51 erg.
Yes.
How accurate that energy is?
Okay, you want to more correct, I would say is about 1.2 10 to 51 ergs of energy. So actually, it's the order, so 10 to 51, astronomers usually order of the magnitude. So 10 to 51 is actually quite good because it's not that difficult to understanding about this number because we calculate this amount of energy. How big is exploding energy? It actually determined by the binding energy of the structures. So the binding energy of the compact, for example, for the compact like a iron core, is roughly about this order. The core is the center, so the envelope, the star is very big, but the core is very tiny, like a 5,000 kilometers. Most of things actually determine explosion is inside that star, inside that core. So you need to make something explode, your energy at least sufficiently unbound the entire structure. although you still need to add additional energy, for example, the fallback of the chunk of velocity of the mass, this kind of energy, but it's roughly at the same order. So that's the code determining the structure. And it happening for most of supernova, like iron core, just 1.5 exceeding transition mass. That's how it occurs. But the how massive star will change because later when you collapse different amount of different mass star, the way they fall in material into the core at a very different speed and different velocity. So that makes quite a difference. Something can easily explode, some star cannot. That's the point.
So second question, you show the MAD2 image in the really first part. That kind of large scale upflow, but how much energy really goes into efficiency of the feedback, and also is that radiative feedback or kinetic feedback?
Oh, you mean the feedback from accreting black hole? In the
no, the supernova, basically MAD2, they have huge amount of supernova explosions in the past, and still ongoing. And what's the efficiency of the 10 to the 51 going into the outflow, and also is it radiative feedback?
Yeah, this is a very good question. Many people confuse. So the key point about how do we know the supernova explosion observationally is 10 to 51 ergs. The way is we measure amount of the mass and how fast they travel, and 0.5 m v squared kinetic velocity. So those of the energy actually.
That's the amount of mass right in the immediate vicinity of the supernova that's emitting the light. You see the light.
Yes. So that's the point. So the supernova explosion energy we get actually is from mainly the kinetic energy of the ejector by measuring the spectrum, the Doppler shift, how fast, and by measuring the mass of these.
Okay, I think the question is you have no clue how much of that actually gets into deep in the gas.
You want to hit the environment.
No, like the MAD2, that
it suffers driven weight outflow. So the question is whether it's radiation, it's driven by radiation or by kinetic energy from the supernova.
I tell you one thing. Okay, this is also a good point. So actually, you calculate the radiation energy, integrate all the entire life of the massive star, say 20 solar mass. All the radiation energy amount available. They roughly also close 10 to 51 ergs of energy. So the star, so that's why massive star important because, for example, 10 solar mass star and 1 solar mass star, the feedback is like at least 2 order of magnitude different in radiation energy. And at the end, 10 solar mass star give you another bump, supernova. So those radiative feedback first create the H2 regime and may drive the sun turbulence. But later the supernova play a dominant role to trigger much larger scale. And that might trigger the star formation and other different interesting structures. So amount of energy 10 to 51 ergs in radiation plus 10 to 51 ergs in the kinetic gas energy effect. So that's roughly the order for the normal supernova feedback for one supernova. But if you have 100 solar mass star, then order will be completely different. But whether it becomes supernova, that's many other details to discuss.
Okay, I think we have to move on to the next section.
Time to come back.
Yeah. That's what I planned to say. Yeah, so we can move all the discussions maybe in the later afternoon session combined with the All right, so let's thank Chen again.
Thank you very much.
So feel free to take like a 2 minutes quick break.